once again. My name is Hamza Lubwama, and still I'm going to take you around in what we call circular motion. So today, like I promised last time, I'll proceed with another derivation. And this time around, this derivation is basically going to look at the acceleration. Remember, acceleration from the normal definition is the rate of change of velocity. But this time around, the acceleration we are going to look at is what we are going to call centripetal acceleration. So still our topic is circular motion. And in circular motion, we are going to look at what we call centripetal acceleration. If you are to define this, it can be defined as the rate of change of velocity for a body that is moving in a circular path, and it is always directed towards the center of that circular path. So what we are going to start with is to derive that equation, or to derive the acceleration for a body that is moving in a circular path. So if I consider, remember we have seen before, you can recall that velocity is equal to omega r. That is the velocity with which a body moves in a circular path. Now if I look at a body which initially was at point A, and this body at point A had a velocity VA. Then this body changed direction at a point B, and at point B it was moving with a velocity VB. And this has changed to an angle delta theta. Then if I prolong this tangent, because the velocity, as you see, is tangential to the curve or to the circle. So the velocity is a tangent to the curve. So at one point, this velocity is at 90 to the curve. So likewise, even this one is at 90. Now, if I look at polygon forces, two opposite angles add up to 180. So if this is delta theta, then here I'll have 180 minus delta theta. So meaning outside here, angles lie on a straight line, I'll have delta theta. So with that, I can extract out a triangle, an appropriate vector triangle. Extract out an appropriate vector triangle of velocity. And this appropriate vector triangle of velocity will look like this. For example, I can start with the velocity VA, or I can start with the velocity VB. Let me start with VB. This is velocity VB, it's going in that direction. Then if I reverse, this is a negative velocity VA. VA was going this side. Now when I make it face this way, I've changed it. So it becomes a negative. So I can design an appropriate triangle of velocities, and this becomes the resultant velocity. So this becomes the change in velocity. Why? Because if they are vectors, this would be VB a vector minus VA a vector. So that's why I'm calling it a change in velocity. So P, Q, R predicts a triangle which is appropriate for the velocity. And like you see, if I look at this angle here, this angle is also changed in theta. So the angle inside here will be delta theta. This is Q, not delta theta. This is not theta, it's Q. Thus, if PR is the change in velocity. PR, if you look at this angle is right here. If you compare this angle with this angle, then AB is an arc. So PR also approximates to an arc. So I can say PR approximates to an arc. And if I'm looking for length of an arc, in the previous lesson, we saw how to get the length of an arc in this case. So if it approximates to an arc, then remember I said the velocity or the speed does not change. So the magnitude of V is the same magnitude of A, VA. So in that case, this V and this V, they behave like the way the radius would behave there. And the distance here, we saw that it is always R delta theta. Now, because of this change in velocity, the velocity here, which is the change, will be V delta theta. So, because it approximates an arc, PR is equal to V delta theta. Now, by definition, acceleration is equal to change in velocity out of the change in time. And this shall be the change in velocity is v delta theta out of the change in time, which is delta t. Now this is my acceleration small a. But remember we said in the limit, as delta t tends to 0, when it becomes very, very small, then what happens? AB ceases as being an arc. It turns out to be a point or a line. And at that point, the delta theta over delta t is approximately d theta dt. And this d theta dt is the same as omega. With that, we can now conclude that acceleration is equal to v times omega. And this is the first equation of acceleration. I can call this equation 2 in circular motion. Then if I recall, we also saw that v is equal to omega r. So I can say acceleration is equal to omega r times omega, and also acceleration can be omega squared r. And this can be equation 3. Furthermore, also one can say v is equal to omega r, and thus omega is v over r. And with that reason, if I substitute, acceleration shall become v over r times v times r. I lose the r. When you look at this is v and times omega, but omega we are saying is v over r. So when I substitute, I'll have this is v times over r times v, and thus acceleration becomes v squared over r. And this becomes equation 4. So equations 2, 3, and 4 are all equations predicting what we call centripetal acceleration. And that is why centripetal acceleration is defined as the rate of change of velocity for a body that is moving in a circular path and is always directed towards the center of that circular path. So that means centripetal acceleration is always to the center. When you wound this bag, its centripetal acceleration is pointing towards my fingers along the string which is holding it. And with that reason, it induces what we call the centripetal force. Centripetal force. Whereby centripetal force, from force is equal to mass times acceleration. We have seen acceleration is equal to v squared over r, or omega squared r, or v omega. Thus, centripetal acceleration can be, centripetal force can be mv squared over r, or m omega squared r, or it can be mv omega. All these can be predicting the equation for centripetal force. This is centripetal force, which can finally also be defined just like any other force. This force is the force that keeps the body moving in a circular path, and that force is always directed towards the center of that circular path. If I'm wounding this bag horizontally, it forms what we call a conical pendulum. So that force that is making this bag rotate in a horizontal circle, because this is forming a horizontal circle, is what we call centripetal force, and is acting to the center where the circle is defined from. With that regard, you would have defined what we call centripetal force. So we can say centripetal force is the force that keeps a body moving in a circular path and is directed towards the center of that circular path. So with that, we would have defined what centripetal force is. We have derived the centripetal acceleration, And now we are ready to see the applications of centripetal force in circular motion plus its acceleration plus the velocity we derived in some lesson earlier. Yeah, so tune in next time, join me in my tutorials, and then we can see the applications of some of these forces and acceleration in what we call vertical circles and horizontal circles. I'm still Hamza, taking you on in mechanics of physics and mathematics. Stay blessed.